Swayam Prabha. Digital India. Educated India.
In this session, I would discuss the importance of parallax and how the same can be used for finding the ground coordinates and the height of a point. Parallax is the apparent displacement in the position of an object with respect to a frame of reference caused by a shift in the position of the observation. A simple experiment will serve to illustrate parallax. If a finger is held in front of one's eyes and while grazing at the finger, the head is quickly moved from side to side without moving the finger will appear to move from side to side with respect to the objects beyond the finger, such as a picture on the wall. Rather than shifting the head, the same effect can be created by alternately blinking one's eyes. The closer the finger is held to the eyes, the greater will be its apparent shift. This apparent motion of the finger is parallax and it is due to the shift in the position of observation. If a person looked through the viewfinder of an aerial camera as the aircraft moved forward, the images of objects would be seen to move across the field of view. This image motion is another example of parallax caused by shifting the location of the point of observation. Again, the closer an object is to the camera, the more its image will appear to move. An aerial camera exposing overlapping photographs at regular intervals of time obtains records of positions of the images at the instant of exposure. The change in position of an image from one photograph to the next caused by the aircraft's motion is termed stereoscopic parallax or Y parallax or simply parallax. Parallax exists for all images appearing on successive overlapping photographs. For example, the images of objects A and B appear on a pair of overlapping vertical aerial photographs which were taken from exposure station L1 and L2. Points A and B are imaged at A and B on the left hand photograph. The forward motion of the aircraft between exposure, however, causes the images to move laterally across the camera focal plane parallel to the flight line, so that on the right hand photo they appear at A dash and B dash. As point A is higher, that is closer to the camera than point B, the movement of the images across the focal plane is greater. The movement of the image B, in other words, the parallax of point A is greater than the parallax of point B. So, this calls attention to two important aspects of stereoscopic parallax. First, the parallax at any point is directly related to the elevation of the point, and number 2, parallax is greater for higher points than for lower points. Variation of parallax with elevation provides the fundamental basis for determining elevations of points from photographic measurements. The fact x, y and z ground coordinates can be calculated for points based upon their parallax. Figure below shows two photographs in superposition. Parallax of objects points A and B are P A and P B respectively. The stereoscopic parallax of any point such as A, whose images appear on two photographs of a stereo pair expressed in terms of flight line photographic coordinates, is P A is equal to x A minus x dash A. In the above equation, P A is the stereoscopic parallax of object point A, x A is the measured photo coordinate of image A on the left photograph of the stereosphere, and x dash A is the photo coordinate of the image on the right photograph. These photo coordinates are not measured with respect to the fiducial axis system, rather they are measured with respect to the flight line axis system. Thus, it is imperative that proper algebraic signs be given to the measured coordinates to obtain correct values of stereoscopic parallax. Having looked at the concept of parallax and how it is represented on a pair of overlapping photographs, now let us look at the geometry of overlapping vertical photographs for parallax measurement. It is the measurement of parallax on overlapping photographs which makes possible the determination of both the horizontal and vertical positions of the ground points. The parallax of a point measured on a pair of overlapping vertical photographs is algebraic difference of the x coordinate of the point measured on the left photograph and the right photograph. Here the x axis passes through the principal point and is parallel with the flight line, while the y axis passes through the principal point and is perpendicular to the flight line. Then P is equal to x minus x dash, where P is the parallax of the point. The figure shows a pair of overlapping photographs taken from two camera stations at L and L dash from the same flying height, and the parallax of point A is equal to x A minus x A dash, and the parallax of point B is equal to x B minus x B dash. Since the x axis of each photograph of an overlapping pair must be parallel with the flight line, then a single photograph may have two sets of axes from which parallaxes are obtained. One set is associated with the flight line to the left and the other set is associated with the flight line to the right. The figure below illustrates the concept of representing flight line on consecutive photographs. Now, let us look at the development of the parallax equations. Supposing two overlapping vertical photographs are taken from the same flying height h above the datum, the distance between the exposure station L and L dash is the air base B. Both h, that is flying height, and B, air base, are expressed in the same units. The image of ground point P having an elevation small h above the datum appears on the left hand photograph at point P, whose coordinates are defined by the flight line axes are x, y. Similarly, the image of P appears on the right hand photo of point P dash, whose coordinates are defined by the flight line axes x dash, y dash. The focal length L small o or L dash o dash is designated by F, and the principal points are located at O and O dash. Point W on the left hand photograph is the projection of P on the x axis, and W dash on the right hand photograph is the projection of P on the x dash axis. The line L dash W dash for the right hand photograph is imagined to be moved parallel to itself to the position L W dash for the left hand photograph as shown. A pair of ground coordinate axes are established in such positions that the origin at the ground position of the left hand principal point capital O and the x axis and the y axis are parallel respectively to the x axis and y axis of the photographs as defined by the flight line. The ground coordinates of point P are capital X and capital Y as shown below. The triangles capital L, capital O, capital W and the triangle capital L, small o, small w, it is found that the distance through similar triangles, the relationship can be built up as capital O over capital L over small o divided by capital L O is equal to capital L small w divided by capital L w is equal to small o w divided by capital O w. If we substitute these values corresponding to the sides, then this reduces to the equation in the form of f over capital H minus small h is which is equal to small x divided by capital X. Now, in the triangle LWP and L capital W capital P, LW divided by the capital LW is equal to small wp divided by capital WP. So, from this equation we can see that LW divided by capital LW is nothing but it is equal to f over h minus small h. Therefore, from these two equations we can find out that WP divided by capital WP is equal to small y divided by capital Y and is equal to f divided by capital H minus h. In the triangles L dash O dash W and the triangle capital L dash small o dash W dash and in the triangles L dash W dash P dash and L dash W P, the relationship between L dash O dash divided by L dash O dash is equal to L dash small w dash over L dash capital W, which is equal to small w dash p dash divided by capital W p, which yields a relationship equal to y dash over y, or we can say that y dash over capital Y is equal to f h minus h. Therefore, from equation 3 and 4 we find that small y divided by capital Y is equal to f divided by h minus small h and y dash divided by capital W this is equal to f divided by h minus small h, or what we can say is that y is equal to y dash. Now, from this we can say that we can see that for a pair of overlapping vertical photographs taken from the same flying height, the distance from the flying line to a point on the left hand photograph is equal to the distance to the flight line to its conjugate or corresponding point on the right hand photograph. There is no parallax. Now, considering the triangles capital L, capital W, capital L dash and capital L, small w dash, capital L, L dash is parallel to small w dash, L w coincides with and is therefore parallel to L w, capital L dash w dash is parallel to capital L w dash. Therefore, the two triangles are similar triangles. Their corresponding altitudes are capital H minus small h and f. Then by similar triangles we can say that f divided by h minus small h is equal to w dash divided by b. Since w dash is equal to x minus x dash, which is nothing but the parallax of the point P. So, now the equation can be written as f divided by capital H minus h equal to small p divided by b. So, from these equations we can now write the parallax equations as h capital H minus small h is equal to b divided by small p multiplied by f, and x, that is the ground coordinate, x is equal to b divided by small p multiplied by the photographic coordinate x, and capital Y is equal to b divided by small p multiplied by the photographic y coordinate. Now, having established the parallax equations, our next foremost task is the measurement of parallax. The most convenient method for making parallax measurements on a photograph is the use of a device called parallax bar or stereometer. The most common type of parallax bar has been shown below in the picture. It contains of a bar which holds a fixed platen of transparent material, that is clear plastic or glass, near the left end and a movable platen towards the right end. A reference mark or measuring mark is located at the center of each platen and on the underneath surface as shown. The movable half mark is moved by means of a micrometer screw, the total movement being about 25 mm to 40 mm, depending upon the manufacture of the equipment. The micrometers is read to the nearest of 0.01 millimeter. A straight line has been drawn on the sheet of paper and the left photograph has been oriented on the paper, so that the flight line is exactly in coincidence with the line on the paper. This orientation may be obtained by laying a straight edge over the photograph and orienting it to the line. The micrometer of the parallax bar is now set to the middle of the range of the readings. The right hand photograph is placed beneath the stereoscope and adjusted for comfortable stereoscopic vision. The flight line on the right hand photograph must coincide with the straight line on the base sheet. Next, the photographs are then fastened and the parallax bar is placed on the photographs. The left half mark, called the fixed mark, is unclamped and moved so that when the floating mark is fused on a terrain point of average elevation, the parallax bar reading is approximately in the middle run of the graduations. The fixed mark is then clamped and will remain there for the subsequent parallax bar measurements on the stereo pair. After the fixed mark is positioned in this manner, the right half mark or the movable mark may be moved left or right with respect to the fixed mark, that is increasing or decreasing the parallax as required to accommodate high points or low points without exceeding the run of the parallax bar graduations. The adjoining figure shows a schematic diagram of the operating principle of the parallax bar, and we can see that the parallax bar is having two platens which are fixed and movable with a micrometer drum which can read observations to the accuracy of 0.01 millimeter. After the photographs have been oriented and the fixed half marks positioned as just described, the parallax bar constant C for the setup is determined. For the setup, the spacing between the principal points is a constant factor d. Once the fixed mark is clamped and the distance from the fixed mark to the index mark of the parallax bar is and the index mark of the parallax bar is also a constant k. So, the parallax of a point A can be expressed as P A is equal to x A minus x A dash, which is equal to capital D minus within bracket k minus R A, and this can be written as D minus k plus R A, where R A is the micrometer reading and the term D minus k is C, that is the parallax bar constant for this setup. Substituting C in the above equation, the expression becomes P A is equal to C plus R A. The equation above assumes that the parallax bar micrometer to be a forward reading, that is, reading increases with increases parallax bars. Should the readings decrease with increasing parallax, the parallax bar is called backward reading and the algebraic sign of R must be reversed. With this, the parallax bar is now set for measurements. So, let us start taking the measurements. First of all, let us determine the air base, that is the distance between the two camera positions in the space. The air base may be computed if the images of the endpoints of a line of known ground length appear in the area of overlap of the two photographs. The flight line is drawn on each photograph and the y axis is constructed at right angles to the flight line at each principal point. The coordinate axes are thus established for parallax bar measurements. The parallax of each point defining an end of the ground control line is determined preferably by means of the parallax bar. The x and y coordinates of the 2 points are then carefully measured on the left photograph. Let the 2 points be designated as A and B. So, then the ground coordinate A can be expressed as capital B divided by the parallax A on the photograph multiplied by its x coordinate. Similarly, y A, that is the ground coordinate, can be expressed as the base B divided by P A multiplied by y A, and similarly we can express the same for the ground coordinate B also. Now, having designated the ground coordinates in relation to the base B, the parallax of the points and their photographic coordinates on the left photograph, what we can do is we can substitute these values of x a, x b, y a, y b in the standard distance calculating formula. D is equal to under root difference of the x coordinates of a and b whole square plus the difference of the y coordinates of a and b whole squared. By substituting these values, it yields the equation as given below. D is equal to under root of b minus p a multiplied by x a minus b minus p b multiplied by x b whole square plus p b divided by p a multiplied by y a minus b divided by p b multiplied by y a whole squared. Since the distance, that is the photographic coordinates, and the parallax are all known, the airbase B can be computed by solving the preceding equation for B. Thus, B can be expressed as distance A B on the ground divided by the x A over P A minus x B over P B whole square plus y A over P A minus y B divided by P B whole square and taking the under root of the same. To verify the value of B, ground coordinates of the 2 points are computed and the distance formula is applied by using the ground coordinates in order to compute the ground length of the control line. The computed length must agree with the known length. Having done the determination of the airbase, now let us look, before we proceed to take the observations of parallax using parallax bar, it is important to understand the principle of obtaining the parallax from a parallax bar, and for that we discuss the principle of floating mark. The ability of the observer to see a stereoscopic image when viewing through a stereoscope is based on the slight variation in the parallax from point to point. It is possible to introduce into the stereoscopic image a distinctive mark that seems to float in the stereoscopic image space. This mark is called the floating mark, and it is the basis for the 3-dimensional measurement of a stereoscopic image. Assume that a pair of photographs have been oriented under a stereoscope for comfortable stereoscopic viewing. This orientation is shown in the figure with the stereoscope eliminated for clarity. A mark of the same size and shape is placed on each of the 2 pieces of the transparent material such as acetate or glass. These marks are now placed on the 2 photographs. When viewed stereoscopically, the 2 marks fused into one image, say at a position 1 shown in the figure. The viewer will experience the sensation that the image of the mark is floating in space above the ground. If the right hand mark is moved slightly to the right and the marks again fused together, the image will appear to have been lowered to position 2 in the space. If the right hand mark is moved still further, the floating mark will appear to touch the ground at position 3. At this point, 2 marks define the exact position of a pair of conjugate points on the 2 photographs. The floating marks to move up and down stereoscopic images causes the parallax of the marks that has been changed by moving one horizontally with respect to the other. In instruments that measure 3-dimensionally, the 2 marks are called half marks and move together through the stereoscopic image and constitute the measuring mark of the instrument. If their separation and thus their parallax is held constant, the floating mark appears to move in the three-dimensional image at a constant elevation. This allows the observer to trace contour lines. Let us now look at the computations of the parallax of principal points. To calculate the parallax bar constant, a micrometer reading is taken with the floating mark set on a point. The parallax of that point is also measured directly monoscopically. Then, with P and R for that point known, the value of C is calculated as C is equal to P minus R. The parallax bar constant should be determined on the basis of the micrometer reading and the parallax measurement for the 2 points. Then the mean of the two values of the C may be adopted. Any 2 points may be selected for this purpose. However, 2 principal points are convenient and often used. Figure shows a section through a pair of overlapping vertical photographs. The parallax of the left photo ground principal point O1 is nothing but P O1 is equal to x O1 minus x dash O1, or it is equal to 0 minus b dash, or it is b dash, as the x coordinates of O1 on the left photo is 0. Since the parallax of the right photo ground principal point O2 is equal to P O2 is equal to x dash O2, which is equal to b minus 0, which is equal to small b. Thus, it is seen that the parallax of the left ground principal point is photo base b dash measured on the right photo, and the parallax of the right ground principal point is photo base b measured on the left photo. To determine the parallax bar constant using principal points, distances b and b dash are first measured. The floating mark is then stereoscopically placed on the right principal point O2, and the micrometer value RO2 is read, from which we obtain C2 is equal to b minus RO2. Errors due to tilt in the photography, unequal flying heights, paper shrinkage and measurements will generally give two slightly different values of C. The mean value is normally adopted. In practice, the principal points sometimes become dephased, so that the stereoscopic measurements RO1 and RO2 are difficult to obtain. In that case, since the parallax of a point depends upon the elevation of the point and not on its location on the photograph, the floating mark may be stereoscopically set just slightly to the side of them when their micrometer readings are taken. This will not affect the micrometer reading if the ground is reasonably level, the principal point, and it avoids the inaccuracy of setting the floating mark on dephased imagery. Alternately, any two discrete images may be used. However, they should be chosen so that they lie on the opposite sides of the flight line and equidistant from the flight line. This minimizes errors in parallax due to tilt and faulty orientation of the photographs. One of the advantages of measuring parallax stereoscopically is increased speed. For one, the parallax bar constant is determined. The parallaxes of all the points are quickly obtained with a single micrometer reading for each point. Another advantage is increased accuracy, not only because binocular vision is being used, but also because the least count of the most parallax bar micrometer scales is 0.01 millimeter. A person's ability to set the floating mark, like learning to swim, improves with practice. an experienced person using quality equipment and clear photographs is able to obtain the parallax to within approximately plus minus 0.03 mm of their correct values. Having found out the parallax bar constant using the principal point, now let us extend this concept for determination of elevations by parallax differences. Parallax differences between one point and the other are caused by different elevations of the 2 points. While parallax equation serves to define the relationship of the parallax stereoscopic parallax to flying height h, elevation small h, airbase b and camera focal length f, parallax differences are more convenient for determining elevations. Let object C be a control point whose elevation hc above datum is known. Let there be another point A whose elevation is desired. So, the parallaxes of both the points can be expressed as Pc is equal to f multiplied by capital B divided by h minus hc and Pa is equal to f into B divided by capital H minus Ha. Now, the difference in the parallax between the points A and C can be expressed as Pa minus Pc and can be obtained by subtracting equation 1 from equation 2 and rearranging. This yields that Pa is equal to Pa minus Pc is equal to f into B multiplied by h small h A minus hc divided by h minus Ha multiplied by h minus hc. Now, if Pa and Pc is equal to delta p, that is the difference in parallax, substituting h minus Ha from equation 1 and delta p in equation 3 and reducing, the following expression for Ha is obtained, that is Ha is equal to Hc plus delta p multiplied by the difference of h minus Hc divided by Pa. So, in this manner the elevations of all points in the photograph can be measured by having the knowledge of or the location of one control point whose heights are available to us. Now, this concept can be extended for mapping the details. So, let us look at the next activity, and that is mapping with stereoscope and parallax bar. When accuracy requirements are low, suitable topographical maps may be compiled using a stereoscope and a parallax bar. One method of accomplishing this is to compute planimetric positions of all the map details and contour points necessary for elevation contours. Elevations of the contour points are preferably determined using parallax difference equation. These points can all be plotted in a planimetric correct manner according to their coordinates. Elevation contours can then be interpolated between the contour points. The mapping procedure described above requires considerable time and work. A much faster method is simply to trace planimetric positions of points directly from the left photograph of the stereo pair on a transparent overlay. Elevations of all necessary points may then be determined by measuring parallax differences. The contours can be interpolated and drawn directly on the overlay while viewing the stereo model through the stereoscope. This affords the operator the advantage of being able to actually see the terrain in 3 dimensions while drawing the contours. Since planimetric positions of the points are directly traced from a photograph, however, this method has a disadvantage, that is, the resulting map is a perspective projection. It varies in scale with terrain elevation and contains all the image positional errors of the left photograph. Another method of map compilation with stereoscope and parallax bar is to use one of the instruments designed specifically for direct tracing of photographic features and elevation contours. One such instrument is the stereocomparatograph. It consists of a mirror stereoscope and the parallax bar mounted together as a unit. The photographs are oriented for clear stereo viewing using the flight line method. The stereocomparatograph may be attached to parallel drafting arm and oriented so that the line through the half marks of the parallax bar is parallel to the flight line. The stereo comparator may then be moved from the stereo model, tracing topographic features such as roads, fences, rivers, etc., by keeping the floating bar constantly in contact with features being traced. A metal arm attached to the stereocomparatograph holds a pencil which enables direct tracing of the features onto a map sheet. With proper parallax bar micrometer readings set, contours may be traced directly by keeping the floating mark in contact with the ground as it is moved about the stereo model. With this, the user will now be able to create a map using a pair of overlapping photographs. In my next session, I will introduce to you another technique of mapping keeping the camera axis horizontal to the ground. Thank you.